So, welcome everyone to the, I think it's the 20th lecture on statistical theory for deep learning. We have proven our first, on Monday we have proven our first result on least squares neural network estimates and the rate of conversion in case that the regression function is PC smooth. So we have considered a special space of neural networks, calligraphic GN, which is a sum of Kn networks Fk, and each network Fk has Ln hidden layers and Rn neurons in each layer, and uses the ReLU activation function. Then I consider the corresponding least squares estimate and a twiddle, which is just the function of this function space which minimizes the empirical or true risk. So it's this function g which minimizes 1 over n times sum I equal 1 to n g of xi minus yi squared. And, well, that's a little bit strange here. And then I made a truncation of this function. So I defined Mn to be, should come back, doesn't come back, why not? I have no idea about that. So we define Mn to be a digrunted version of this least squares estimate Mn twiddle. So I choose some beta and greater equals 0, and that Mn of x equal to Mn twiddle of x if Mn twiddle of x lies between minus beta and beta n, otherwise I truncated it plus beta n minus beta n. Then we have proven theorem 4.2. We have PC a beta greater 0. We have xy, x1, y1, and so on are IID minus random variables whose values in the cube minus a with exponent d, that's other x, and the closed interval minus beta beta. I assume that the regression function m of x, conditional expectation of capital Y given capital X equal to small x, is PC smooth. I choose, because I know my regression function or my data is bounded by beta, I choose the truncation operator beta n equal to beta. I choose k and ln Rn in a special way. Ln is just a log n, Rn is just a constant, and Kn is n to the power, is of order n to the power d over 2p plus d. And then the expected L2 error is bounded by some log factor times n to the power minus 2p divided by 2p plus d. This is really strange here, yeah? But I think you have seen now everything. Oh, yeah, still can see it. And what we will do next is this a good upper bound? And of course now you can try to improve this upper bound, try to change your proof so that you get a better bound. But what you can do instead, you can also look at lower bounds and try to show that, and with these lower bounds you will actually show that no estimate will achieve a better bound, and that's what we are doing next section. In section 4.3 on lower bounds on the rate of conversion. And what I will present here is a classical result from Charles Stone from the year 1982, so a little bit more than 40 years old, which determined basically, or which introduced minimax rate of conversion, or optimal rate of conversion in the sense of the minimax using the minimax principle, and then determines the optimal rate of conversion for estimation of a PC smooth regression function in D dimension. And I start with the definition, where I introduce this lower minimax rate of conversion, upper minimax rate of conversion, and optimal minimax rate of conversion. So I define this rate of conversion for classes of distribution. So I let D, calligraphic D, be a class of distribution of xy. And my rate of conversion is actually a sequence describing how quickly my expected L2 error will converge to 0. And this sequence I call IN. This is a sequence of positive numbers. If you have attended the lecture on mathematical statistics, then you might remember the minimax principle to define optimal estimates. You look at some kind of error. What we look here is the expected L2 error of our regression estimate. You look at you restrict the distributions. In mathematical statistics, was always some kind of parameters, but here it's just a class of distribution. This is calligraphic D. And then we looked at the worst error within this class of distribution. So we looked at the supremum over all xy of the expected L2 error of our regression function estimate if the regression estimate gets the sample of size n of this distribution xy. And then we try to minimize this guy. So we take the infimum over all estimates and want to determine a regression estimate MN such that it's, for this estimate, the maximal error within this class of distribution is equal to the minimal maximal possible error, or minimal value which you can get. You can consider the whole thing as a game where you play against nature. In the first step, the nature chooses a distribution and gives you a sample of this distribution. The restriction is this distribution is from the class D. In the second step, you can choose regression estimate and try to estimate the corresponding regression function. And then the aim of the nature is that the expected L2 error is as large as possible. The aim of U is that the expected L2 error is as small as possible. And if you if both plays optimal, then you get something what we call here the optimal minimax rate of conversion. But we will do this asymptotically, so we don't make it for fixed n. We have an additional limits for n tending to infinity. Okay, here comes the definition. Our AN is called lower minimax rate of conversion of D. Rate of conversion will be found here. If and maybe I first write down the formula and I'll explain it. We look at the limits inferior. sample size tending to infinity, the infimum over estimates, the supremum over our distribution in our class, and then the expected true error of our estimate. We divide this by an, and it's a lower minimax rate of conversion if this converges to something which is greater than 0. So if this is instance C1 greater 0. So you could also define it for fixed n, then you could forget about this this constant, and you will show that the infimum over all m and the primum over all xy expectation of this one is greater, equal than some constant C1 times a. And that's what we will actually show, so we will actually solve the problem for finite dimension, for finite even. But here I ignore constants and the rate of conversion. First thing, the second, and here the infimum is the infimum over all regression estimates, Mn, which gets a sample of distribution of xy. Please?
So we choose x and y, but in the thing we calculate, we only have x, not y.
You choose x and y, but in the thing you calculate, we only have x, not y. Not true, because this one, Mn, is Mn of x, comma, and depends on x1, y1 up to x and yn. And the deal is that this x and yn up to x and yn are distributed independently as xy, and that m of x is the corresponding regression function. Okay? So it's implicitly written here. First thing. Second thing, aim is called upper minimax rate of conversion. Well, it's called upper minimax rate of conversion if you can find some estimate, so if there exists some estimate Mn such that this supremum here has a limit superior greater than infinity. There exists an estimate Mn, this. Basically, it's a sequence of estimates. And then you look at the limit superior. From the supremum. X prime d. If this guy is equal to some constant C2, less than infinity. And then you see, next thing is, of course, an optimal rate of conversion if it's a lower and an upper minimax rate of conversion. That's the natural thing to do. It's called optimal minimax rate of conversion. if AN is a lower and an upper minimax rate of conversion. Simultaneously. Lower. And an upper minimax rate of conversion of D. And of course, this minimax rate of conversion is not unique. You can change it by some constants, or by some, you can change it by some constants, of course. If AN is an optimal minimax rate of conversion, then 2 times AN is also optimal rate of conversion. Of course, it looks a little bit impractical because it's just for sample size tending to infinity, but what we actually do, if you look at our proofs, and this was 1982, but what we nowadays actually do, we do this even for finite n. So I could also formulate it for finite n and say lower minimax rate of conversion without any limits infinitor, it should be greater than C1 times AN, and otherwise C2 times AN, where C1, C2 do not depend on n. We actually will have this in the proofs. And now if you look at our previous result, our theorem 4.2, then we actually have proven an upper minimax rate of conversion for a class of distribution because we had some bound, the expected true error was less than some constant times log n with power 4 times n with power minus 2p over 2p plus d, and then you can figure out what does the constant depend on. But if you define this class of distribution such that, what did we have? X was bounded and Y was bounded and M was PC smooth, then we had something like this where it depends on the bounds, and the values, the constant depends on the bounds for x and y, and also on the p and z, but on nothing else, and the dimension, of course, but nothing else. So we had something like this here actually. And then the second point is, as I told you last time, we can modify the proof such that we get it also for unbounded y, and that's important because I will show the lower minimax rate of conversion for normally distributed y. Therefore, I need unbounded y. So the following remark, so theorem 4.2 basically shows, and with basically I mean that I have to modify the proof such that that this remark is valid. If D is the class of all distributions, x, y such that well, I assume the boundedness on x, and I assume for simplicity it's in the unit Q. I replace the boundedness of y by some sub-exponential moment. So I assume that the expectation of E1 times y squared is less than infinity. And I need that m is bounded. And well, depends on what. and I should have introduced it, that's the regression function. SPG smooth. And then we have basically showed that log n with power 4, so log factor times n with power minus 2p over 2p plus d is an upper minimax rate of conversion. Log n is power 4 times n is power minus 2p over 2p plus d. It's an upper minimax rate of conversion. And what I show next is that if I forget about the log factor, and I told you the log factor is not optimal, then this is actually a lower minimax rate of conversion. We show minus 2p plus d. So this guy is a lower minimax rate of conversion of d. And more precisely, we will not show that's a low minimax rate of conversion, or we show that's a low minimax conversion of d, but what you actually do for this, you show it's, because if you want a lower minimax rate of conversion, if you have a lower minimax rate of conversion for one class of distribution, then of course it is also a lower minimax rate of conversion for any superclass of this class. So you can make the d larger. So I can, if I look at the lower roundbeds, I can look at subclasses for d. So more precisely, for some equivalent subset of d. And that's the first thing which we define now, and that's my second definition here, definition 4.2. I have PC greater 0, and at dpc for PC greater 0. The class of all distributions. XY satisfying well, the first condition is X is a uniform distribution. So I make the uniform distribution on the unicube. First condition. Second condition, I define my y as a function m of x plus some random error n, and this random error n is standard normal distributed and independent of x. is n0, 1, and xn independent. Then third, my regression function m is PC smooth. And the bound is conditional m. M of x is bounded by 1 for all absolute value. Now you can check whether the assumptions are satisfied. Well, of course, this is satisfied, yeah. Of course, this is PC smooth. Because if you compute here the conditional expectation of y given x, then this is the conditional expectation of m of x given x plus the conditional expectation of m given x. Because n and x are independent, it's the expectation of n and the expectation of n is 0. So this is the conditional expectation of m of x given x, which is just m of x. So m is the regression function. So this regression function is PC smooth, and then you just have to consider whether this quantity is true. But you plug in m, then you plug in y, then you see the m of x doesn't matter because it's just a constant. So you basically need that expectation of constant 1 times n squared. Of the expectation of e of constant 1 times n squared is less than infinity, and that you can easily verify. It's true for if n is standard normal for, I think C1 equal 1 if you plug in the density of the, or maybe you see the C1 a little bit smaller than 1 if you plug in the density of the standard normal distribution. So this kind, therefore this is called subquotient because it's especially for normal distribution satisfied. So this is subclass. And now you can imagine what the theorem is. The theorem is n with exponent minus 2p over 2b plus d is a lower minimax rate of conversion of the class DBC. That's what we should. Us. So the main result, which we proved in series 4.3, which goes back to Charles Stone from the 1982. Actually, was any of you born in 1982? I don't think so yet. I was not studying mathematics at that time. So we let PC greater 0 and define dPC as above. Then this n with maximum minus 2p over 2p plus d is a lower minimax rate of conversion of DPC. And actually, the result in Stone 1982 was it's the optimal minimax rate of conversion. So he did not only define the lower minimax rate of conversion, but also proved an upper minimax rate of conversion. Also for a slightly stronger class where the distribution of x actually has a density with respect to the Lebesgue-Morel measure, which is 0 outside of the unit cube and bounded away from 0 and infinity on this unit cube. We proved that. And then you see the rate which we got cannot be improved by more than log factor. And regardless what kind of estimate we use. This is not about neural networks, this is about any estimate, which is a nice thing. Questions so far? Then maybe I'll make a 5 minutes break for cleaning the backwards. It's 10:22 on my clock, so I go home at 10:27. I would like to go on. So we have a theorem, now we need a proof, and for the proof I need some additional lemma, which you don't see at the moment why this kind of lemma you will need, but you will see it in the proof. The proof I will give the next time, the lemma I will do today. But the lemma is interesting in itself, I think. It's possible to understand the lemma. But you don't see at the moment the theory. The lemma is it's not the way Charles Stone has proven it in 1982. The way Charles Stone has formulated it was for the lower bound a little bit more complicated, because he looked at tail probabilities. So he looked at the probability that the L2 error is greater than some constant times the rate of conversion, something like this, which is for the lower bound harder, but for the upper bound easier. And we make an easier proof for the lower bound. And then if you look in the original paper, you don't understand the proof. That's some kind. But here that's rather simple because of the following lemma. I consider the situation where I give you some data. The data consists of a L-dimensional standard normally distributed random variable. So you have L standard normally distributed real components, and they are independent, plus some vector u is an RL, times some sign. The sign is +1 or -1. And I choose the sign randomly from a uniform distribution of +1, -1, independently of the standard normal distributed. And then from this vector, from this observation, you should tell me what the sign is. And I consider what is the lower bound on the probability, or I determine actually the optimal probability of error you get. Let me formulate it. You have an U in RL. Let's see. Here, random variable. Well, with values in -1, 1, but I can skip this if I just say that C takes on the value 1 with probability 1/2 and -1 with probability -1/2. Because then almost surely the values are in -1, 1. Now let n be an L-dimensional standard normally distributed random variable independent of C. Standard normally distributed. Independent of C. This means that n is equal to some n vector of n1 to nl, which are independent standard normally. N is equal to, I wanted to write n here, actually it's 1 to nl. Independent M01. M01 distributed. And NC independent. So that's the setting. What I give you is an observation set. That's C times U plus N. That's a random variable in RL. And what I ask you is to use this set to tell me what's the value of C. Is it +1 or -1? How to do this? Well, this means that you have to find a function, I call it here G, from RL to intersect -1, 1. And you look at the probability L star, which is the minimum over all G from RL to -1, 1 of the probability that G of Z is not the same as C. And then I want to know how large is this quantity. And surprisingly, of course, it's not clear. Does this minimum exist here? Of course, I need here measurable functions. I don't know. But you will see from the proof the minimum actually exists, because I will construct such a function. And it turns out it's standard cumulative distribution function of the standard normal distribution of minus norm u. So that's the claim, where phi is the CDF. Cumulative distribution function of N0. You don't see any relation at the moment with theorem 4.3, maybe ignore it, but I guess you understand the problem. You observe ±1 value random variable, C times a vector u plus some standard normal distribution, and you want to say what the value of C is. And it turns out, if you determine your predictor in an optimal way, the error probability is just phi of minus norm. Questions? Please?
So the Z is defined as what you did up there, or is it, did you say the observed in the direction?
You mean this one, the set? Yeah. The set is defined this way.
It's defined.
It's defined this way. It's in Z. And that's what you, so I could also write in here, instead of Z, and we will do this in the proof, C times U plus N, yeah? That's probability we're looking at. Any more questions? Well, okay, then let's prove it. And I have to confess, this is one question on the list of excellent questions, sorry for that, but it's an easy one. And if I make these conversions and you are already shocked, I can shock you even more, because theorem for 3 to prove is only 2, which is not worse. But okay, so which means I'm not allowed to look in my lecture notes to prove it. But you will see it's actually totally easy, this proof. Because what you actually do, you just compute this probability. Well, why can you compute this probability? You can compute this probability while you plug in the value of Z here, and then you know the distribution of C and the distribution of N, and they are independent, so you know the joint distribution. So you can compute this probability. And then you minimize this probability from fixed G with respect to a function. That's the point. So that G be arbitrary. Then we look at this probability. G of Z not equal to C, which is of course the same. I just plug in the C, the definition of Z, C times U plus N not equal C. And now you know that C takes on only the values minus 1 and 1, and it's independent of n, so it somehow makes sense that you distinguish here the cases C equal to 1 and C equal to minus 1. Which is the probability, and either of two will happen. C equal 1 plus the probability that's minus 1. And now, in my probabilities, if I know that C is 1, then I can, of course, replace, in this time, C by 1. And in this time, C by minus 1. So what happens then? Well, if C is 1, then it's G of C is 1, so it's U plus N. It should be not equal to 1. G takes on only the values minus 1, 1, so it must be minus 1. Now we make the same with the other one, this G of minus U plus N. Should be not equal to minus 1, so should be equal to 1. And Z is minus 1. And guess what? You have two conditions, they are independent. Because N and C are independent. So it's just a product. So it's G of U plus N is equal to minus 1 times C equal 1 plus probability of G of minus U plus N equal 1 times probability of C equal 1. And now you minus 1. Now you know Z takes on the values plus 1, minus 1 each with probability 1/2. So we plug in this one. So we are at this line 1/2 times probability of G of U plus N minus 1 plus 1/2 times the probability of G of U plus N equal 1. Now we know the distribution of n, then we can compute this probability here. How to do this? Well, first, what do we know about n? N is L-dimensional standard normally distributed, so it has L components which are independent real-valued standard normal variables. What can you tell me about the density of n? N has the density. Say x, why not x? Say 5x. And x has components x1 to xd here. What do we know about the density 5? So for x, now it's x1 to xl. We have this one here.
It should be the product of the densities of n1 till nl.
It should be the product of the densities of the L components. So we have product, maybe I call it I equal 1 to L. And now you need the density of the standard normal distribution. It's 1 over square root of 2p, 2 pi, times e to the power minus Now the component, the value is xi squared half. Now you use the first one gives you 2p is exponent L divided by 2 product, and then the second one, the product of the exponentials, is the exponential of the sum, and the sum is e to the power minus norm x squared half. So we have this one. Now I would like to there's something wrong here, yeah? Sorry, I made a mistake. Here I have a u and a minus u. So I also need here a u, that's correct, but I need a minus u here. And congratulations, you didn't tell me this too early, but sometimes this trick doesn't work here. But I think my analysis professor was more funny guy than I was, because he once told us that he prepared his lecture at 4 in the morning, and I think this lecture was like it was prepared at 4 in the morning or 5 in the morning. Yeah? My lecture would be prepared at 5 in the morning. Yeah? Much more funny. Okay. But he was a famous mathematician, a lot of third-party projects, research projects, and so on, and busy all the time. But then you have no time for preparing a lecture. Okay, so we are here now because what I want to know now, what's the density of u plus n? And I want to know, and then I want to also know the density of minus u plus n. Any idea what the density of u plus n is? In the norm, you have just x minus u. Right. What you do is, well, it's one point is to look at it's L-dimensional standard normal distribution shifted by u. So the center is just instead of 0 is u, but you also could make it components-wise. Then for each of these components, you have shifted the expectation is no longer 0, but the expectation is ui. So you have to subtract ui here. And then you see it's xi minus ui squared, and this gives you, so it actually gives you just phi of it actually gives you phi of x minus u. No? Yeah. It's this guy. And minus u plus n has density correspondingly. Just replace u by minus u, x plus u. And in the lecture note, I propose to consider the cumulative distribution function, but I'm not sure whether this actually helps. Maybe it's easier to see it directly. Maybe the easiest way is to add this u to each of the components of the standard normal distribution. You see it most easily. Okay, but now, and now I can compute the probabilities. This implies what I'm interested in is the probability that this was g of z is not equal z. I can now write as a sum of two integrals. The first one is 1/2 times, and well, you consider the expectation, that probability as the expectation of the event, of the indicator function, that this value takes on value -1, and then I plug in this, replace this one by my variable which I integrate, and add this density. And well, okay, I call it x. It's expectation of RL indicator that my g of x is equal to -1 times density of x. So the density here is phi of x minus u x plus the second integral. The indicator is this time g of x is equal to +1. And my density of minus u plus n is phi of x plus u. And I combine both integrals, and I get the sum of two terms. Integrated g of x equal to -1 times x minus u plus indicator g of x is 1 times phi of x plus u dx. And we have computed our probability for some arbitrary function g. Questions? Please?
Okay, why should then there be a minimum? We just have a value there.
We don't have a minimum at the moment. I just computed this probability for an arbitrary g. That's all. Next, we want to determine the minimal value.
Okay. I just thought from mentioning what you mentioned earlier
That the minimum exists, yeah? Well, we can see if what we next try, and this will be my next question, how you can minimize this integral with respect to the function g. So the question is, can I give some lower bound here? Of course, I can give it a lower bound 0 here, but maybe something more. Or can I actually give a lower bound and see the function which achieves this lower bound? And that's what I want to do. And the trick is, you don't minimize this one with respect to the global function c, you minimize it pointwise. So for each x, you minimize the bracket here. And if you minimize it pointwise, then of course, then you have to determine the function value for each x, and you have the function which minimizes it. And I think it's easy to see what the minimal function is, huh? Any idea? Or maybe I clean the blackboard over there and you can think about it as long. Okay, any idea?
Yeah, so for each x, I want to, I have to decide if I take the left summit or the right summit.
Right, for each f you have to decide whether to take the left summit or the right summit.
Yeah, of course I always want to take that summit which is lower, so...
And you talk that summit which is lower, so you talk, take the value -1 if this one is the smaller one than this one, yeah? And +1 if this one is the smaller one. So the integral is minimal for g star of x. It's 1 or -1. And if it's 1, it's 1 if phi of x plus u is less than phi of x minus u, correct? Yeah. And otherwise, phi of x plus u greater or equal to phi of x minus u. And it doesn't matter where I write the equality here. So we found a function exists, and we found it. And now for this function we have to compute this integral. And it's easiest if you first write this function in a more finer way by looking a little bit closer what this means. Because of, we look at phi of x plus y, x plus u is less than phi of x minus u. That's the same, well, you just plug in the value. We know what phi is, so it's 1 over 2p with exponent L half times e with exponent minus norm squared of the argument. The argument is x plus u divided by half. That should be lower than same factor, half times e with exponent minus norm x minus u squared half. And now, of course, I can forget about this factor here. I can multiply with, or this is 1 over e, so I multiply on the other hand. Then you have the exponential of x minus u, norm x minus u squared half should be less than e of x plus u squared half, which just means that the arguments have this relation, and you forget about the factor 2, and then you get, so the norm of x minus u squared should be less than the norm of x plus u squared. And then you, well, the norm of x plus u squared minus x minus u squared should be greater than 0. You multiply out the norm squared using the scalar product. Then you see the x squared, the norm x squared, and u squared is cancels. So you have 2 times the scalar product of xu minus 2 times the scalar product of x and minus u, which gives you 4 times the scalar product of xu. So basically, the scalar product of xu must be greater than 0. And now you see you have an easier form of G star. G star of x is 1 if the scalar product of xu is greater than 0 and minus 1 the scalar product is less than 0. Less than 0. If this one. And I guess if you look for a long time on lemma 4.1 and think about it, you will immediately see that's the right thing to do. But it makes sense that you look, basically you look at the scalar product of your observation with u. So you need to know what, but here to use this rule, you need to know what the vector u is. Okay, any questions so far? Now we use this G star to compute again this probability and see what happens. Before I have to clean the blackboard. So hence we have our L star is just the probability that G star of Z is not equal to C. And now we make the same thing as we do here with G star instead of C. Above. And then we get on the right blackboard, left part, the upper line. This is I just write this one with G star, 1/2 times the probability of G star of u plus n is equal to -1 plus 1/2 times the probability of G star of minus u plus n is equal to 1. And now I can plug in the definition of G star. Half times the probability. Well, G star of u plus n is equal to -1 if the argument, scalar product between the argument and u is less equal than 0. So it means scalar product of u plus n and u must be less equal 0. That's our first probability. And the second is just the scalar product of, here it should be 1, of minus u plus n, and u must be greater 0. And now you use the linearity of the scalar product. That's the scalar product of u with itself, so it's norm u squared plus scalar product of nu. So that means that's the probability that the scalar product of n and u is less equal minus norm u squared. And the other one is the probability of n and scalar product of n and u is greater of norm u squared. So we're here. And that we have to compute. And you know the distribution of n. N is an L-dimensional standard normal distributed random variable. What do we know about the distribution of the scalar product of this random variable and some vector? Now I need your basic knowledge of probability theory. Ever heard about scalar products of multivariate, normally distributed random variables with real vectors? Well, not in my lecture because we never deal with the multivariate, normally distributed random variable here. But this is our L-dimensional standard normally distributed random vector is a vector of components which are independently standard normal. And if you make a scalar product with some vector, what do you get? just compute a scalar product. You need to make the first component of your vector times the first random variable plus the second component of the vector times the second random variable. So you get a linear combination of independent, standard, normally distributed random variables. What do we know about them? What do you know about linear combinations of independent, standard, normal variables?
Yeah, again, no standard, not standard, but normal distributed.
They are normally, so the linear combinations of independent, normally distributed random variables are normally distributed. That was one of the things we, I don't know, I guess you see it easily if you look at the characteristic functions, because the characteristic function will be just a product of characteristic function and everything will turn out. So we know that this is a normal distribution, we just need the expectation and the variance to compute it. And the most simple thing to do this is to divide by norm u, but that's not possible if u is if the norm is 0. So we consider the case separately. If norm u equals 0, then L star, well, u is the 0 vector, that's 1/2 times that's 0, less equals 0, that's 1. This probability, and this is 1/2 times, and this is 0, should be greater than 0, that's never happening, so it's 0, so that's 1/2. And that's phi of minus norm u. So we have proven our assertion. So if then I divide this whole thing by norm u, and then I get the scalar product of L u divided by norm u, which is the scalar product of n with some unit vector. And now this is normally distributed, first point. Second, what's the expectation? Zero, because all the components of n have 0 expectation. What's the variance? Well, because if you compute the variance, yeah, you just have a sum of independent normally distributed, standard normally distributed random variables times some factor, which gives you the variance of a sum of independent random variables is the sum of the variances. For the variance, you can plug out the factor as squared. And this variance of the components are all 1. So, and this norm of the, and this sum of the ith components of u squared divided by norm u squared, sum I equal 1 to L gives you out 1. So, this is n01. 01 distributed. Since it is normally distributed, as a linear combination of independent normally distributed random variables. And with expectation 0 and variance 1. So hence, we look at a star. I divide in these probabilities by norm mu. It's 1/2 times das kann man gut. Then you see the random variables which we have are standard normal. The first one is just the cumulative distribution function at the point minus norm mu. So it's 1/2 times 5 minus norm mu. And the second one is if you look at the complement is of this probability, the probability of the complement of this event is just the standard normal distribution, cumulative standard normal distribution function at the norm mu, so that's 1 minus 5 norm mu. And if you know about the symmetry of the density of the standard normal distribution, you know this implies some symmetry of the density of the cumulative distribution function. So these two guys are equal. So that's just 5 minus norm mu. And we are done. Questions? Question? Okay, let me see whether this beamer is now working. Maybe yeah, it looks like. Because I wanted to show something. Oh yeah, there was an advertisement which I should show. I could show this advertisement. This advertisement session. There's a Meet the Beamies on 2nd of July. So if someone is interested to see what, or want to talk to people who are making a PhD here as a teaching assistant, then there's some information where you can go to July 2nd at 15 o'clock afternoon in the room 244 in our building. But I have more to show, sorry. That was just a well, I don't get money for this thing, so I can't tell you. Yeah, it's here. Because I have the survey on the lecture, which you filled in. And unfortunately everything is in German, but I think I show you the summary of the questions, and you see it's something, well, the most critical questions are good, but some of the questions are also very good. So for instance, which is a critical question? Oh yeah, one point was you didn't, the second question about the aims of the lecture. You did not realize the aims of the lecture. Maybe I should have told you this, yeah. But it's basically it's simple, yeah. You learn what you need to write a master thesis about deep learning in statistics, and you also learn about the field. The other one was, oh yeah, nice thing is always this question: Is it well explained? It's 2.8, yeah, it was good. This could be a little better, yeah. But I think it wasn't my best lecture, because it was a rather technical proof. And then, what was... Yeah, how much the second last line, how much did you learn? Not much. That's something okay, I can improve. And I think there should be also an overall mark of this lecture. Oh yeah, does your interest on this topic increase or no, not at all? Well, the good news, which I can tell you here is, clearly the good news is, my salary doesn't depend on your answers. Otherwise, would be a kind of problem. Okay, and then there were also some comments, what was good, what was bad, and what did you like, and of course what was useful, the lecture notes, the recording, the practicing course, what did you like, the recording, very often the list of exam questions, because you can use them rather, you can use them for preparing the exam, and that's right, yeah, because it explains a little bit more clearly what I expect for you for the exam. That makes sense, and especially for oral exam, if I don't make a list of oral exams, if I don't make a list of questions, then of course I will have some implicit list of questions, and you can just learn about this if you ask some other students which have done such an exam in the past. But then you will get they did not really realize or don't understand complete the questions, and then they give you wrong questions, and that's what I want to avoid here. Okay, what didn't you like? The quality of the sound of the videos could be better. That's correct, but I just did not manage it technically. It's a very simple thing what I'm doing here, and as you might have realized, I managed to record all the lectures without any failure, which is not always the case if you do it with the e-learning center, for instance. And also the e-learning center, they would come up with a student and would focus on some part of the blackboard, because they have a worse camera than I'm using here. And I think that's actually worse, because you don't see everything at all. Okay, and then more applications that could be true. And sometimes I'm talking too fast, that's always the case. Okay, that's what I want to tell you for today. Any questions on your side? Then we will do the main proof of the theory next lecture on Monday. Thank you very much.